Hello, everyone. Come on in. Come on in.
Can I get a quick question out of the way?
Yeah, go for it.
So, about Thursday, I recall you talking to my group specifically about section D regarding the telescope. I just wanted to make sure before I set anything in before the due date.
Yeah, you didn't have to go.
We're not supposed to do D, right?
Not anything. Nope. No, nothing on the telescope part.
Okay, that's just what I wanted to know.
No problem. It's scary at the last second when you get returning thing and you're like, ah. So far, we only got 6 people.
You did say that, right?
Yes.
Yeah, I should check again.
Yep, no telescope part. Anybody have any other questions? Only got 6 people here right now. I hesitate to start with so few. Oh, we're getting the 7th. Life is getting good. Getting fabulous.
Yeah, I bet they're all going to jump in the next few seconds.
Yeah, I hope so. I hope I don't have any problems. Yesterday, both of my classes got screwed up by, I don't know what happened, but our internet was bad, at least in my end of the line. I think that's what it was. So both classes I had to make a bunch of videos for them. I did 2.5 hours of extra meeting time this morning, just as like sort of office hour type thing, but I did it by Zoom so we could help them. But nobody showed up for the first hour, so at least they got out of that.
And just for a quick clarification, so I know the homework, their dates are always being pushed back, so I'm guessing those dates aren't accurate.
The ones homework. Actually, as of yesterday, I've set them all to what I think is likely to be correct, but I did that late last night, so you might not have seen them yet.
And also on the lab, now you mentioned the telescope portion, but I thought you said you were sending out an email as well. I didn't get it for some reason. But
yeah, so the telescope part is the most important part. That's the only thing you have to turn in this time. No, we omitted the telescope part. I just finished talking about that, so I thought it'd be funny. It's funny because it's happening to you. No, Clarence, nothing.
Okay.
Yeah, me too.
All right, I was frozen there for a second. Yeah, did y'all hear everything? No, Clarence, did you hear my joke, or did you just hear the horrible mean part and then not me straightening it?
Yeah, actually, you did cut out before you could straighten it.
Yeah, so I heard nothing.
Sorry about that. I was just laughing, having a good time, and I was sitting there thinking, I was looking at myself and like, man, I'm not moving. So yes, the telescope part was completely omitted. We didn't have to do anything, but I like to tell people that that it was the most important part. It's the only part you have to turn in. You get 0 if you did anything else. I was like, man, this is a bummer. He's not laughing. Oh crap.
Yeah, I was like, wait a minute, I just completely misheard him. Like, wait.
I did the same thing the other day at McDonald's. I try to take these people that are actually coming to work and they're all understaffed at fast food joints. And I try to, make a joke or something just to make them a little happier because I feel so bad for them. I pulled up and I had like 2 Happy Meals and a large drink or something like that. And he said, do you have 2 Chicken McNugget Happy Meals and large drink? I said, no, I had 12 Happy Meals and 3 were cheeseburger, but the other 9. He said, you said what? I said, no, I'm just messing with you, man. Yeah, you got my. And then I got my order and it was all wrong. So then I felt bad. I was like, well, that might have been my fault. Hopefully our connection stays stable. Obviously Zoom was having a problem with it. But does anybody have any questions on course material or anything like that before we get started on chapter 31?
I heard you briefly talk about the mastering physics and whatnot. So for all the stuff that, I know you said you had adjusted the dates and all that, but just to make sure I didn't get the late penalty, I had tried to read ahead and do some of the homeworks anyway. And right. So the grades were already in. Is there any way that those could be reopened for the people that have done them without us covering the material in class? I know that obviously that was something that probably shouldn't have been done on my part, but.
Let me check. I mean,
Yeah, because
Because the problem is if I erase it, then you lose the grade that you did get. And if you got a better grade a better grade the first time, I'd feel bad about that. But yeah, let me see what I can do. I opened up the things that had closed early. So they now have the date set later. So for instance, I've already set dates for chapters 17, 18, 19, 20, as well as the extra credit ones. And all the extra credit ones I set to be due at 11:59 p.m. on December 15th.
Yeah, I'd seen that you changed the dates. I was just curious if like the people who had done it, because I had seen in Canvas that I'm not the only one. There's a bunch of averages in there and whatnot. So I'm assuming other people had done it as well. Let me see.
I think I can download them and keep those scores. If just let me know if you're one of those people. That way I can make a point, because it's a lot different from downloading everybody versus downloading one or two people. So it might be a difference of, a 30-minute job versus a 4-hour job. So if you let me know if you happen to do any of those, and I will specifically clear yours out, record yours. And then if your grade turns out to be worse next time, then I'll give you the old one.
Okay.
I mean, it
sounds good. Yeah, I was just curious about if it's too much of a hassle or whatever. I mean, I didn't get a bad grade by any means, but I think I did hit like, just not what I was expecting to do if we had covered it in class.
Yeah, I would imagine you did. The homeworks are really, they're supposed to be harder than the test. That level of work is supposed to be a higher level than the test work.
Yeah, it definitely wasn't easy. That's for sure.
No problem. And it might even be something. Try also, before you do that, see if you can do them now that the date's been pushed back, and see if it automatically just updates your score. If it gives you the higher of the two, or if it doesn't penalize you or something like that, then I'm okay with it, and we'll keep that. But if you don't see that's happening, definitely let me know, and I will clear your score out and give you a blank slate to try it again.
Okay, sounds good. Yeah,
everybody email me on that, and if you did that.
Yeah, I'll check it out, and then if I can't adjust it or reattempt it, then I'll send you an email.
No problem. Thank you.
Thank you.
Anyone else?
I was gonna say, you mentioned chapter 20 and a couple of them in the teens. But chapter 20 is conceptual is still due today. I'm assuming that's not correct.
No, that shouldn't be correct. In fact, I probably didn't even see that there was a conceptual for chapter 20, because I didn't find the chapter 20 at all until like the last thing, and that was for the homework, and I just clicked it on at the last minute, and I don't even know if it's a chapter that we cover. So
also,
there's a chapter 20 and chapter 39.
Gotcha.
Exactly. Yeah, chapter 39 is also due today. And
did anybody see what? Well, I'm wondering if anybody saw what chapter 20 was, because we do. Normally, my other cohorts at TCC do not cover the second law of thermodynamics. I do a quick and dirty version because I can't see teaching a physics course without the second law of thermodynamics. So that is the second law one. And then I want to double check. So yeah, I do 17, 18, 19, and then I do a quick version of 20 usually. And then we're supposed to jump to quantum mechanics, which is 37 and 38, and ideally 39, but I'm not sure we're ever going to get to 39. So that should come open. But yeah, 39 is already a deadline. That must have been another one that I missed, but I was trying to get all of them last night. So we haven't covered them. I'm definitely going to push the dates back later than now. Whatever that happens to be, I'm not sure, but I'll adjust that. So yeah, 37, 38. And normally what I do is I make up a separate little practice test for just the quantum mechanics portion. And so you'll know what I think is important. And I can cover that really quickly. And then you guys do that. And that's all you'll be responsible for quantum mechanics. So that makes it a little easier, a little nicer. But you can see the videos, of course, that I've put up there already on quantum mechanics. Those are pretty helpful. Anyone else? Wow, we got 15 people in here. I am on fire.
So just to clarify, there should be no homework due today.
Unless it was something from like chapter 29 or 30 maybe, but that's it. But I think the 29 was long ago, and 30 might still be open and be due today, but nothing beyond 30. Do you know what's showing right now?
Yeah, chapter 30 is tomorrow. That's what I was saying. Chapter 30 you still have till tomorrow to get done.
Yeah, I think that's reasonable for y'all to get that done by tomorrow, just because, like I said, we did do a shortened version to some extent. But Do y'all feel like that's okay, or y'all feel like y'all not ready for that? I could push it to Sunday, but then you'd have multiple things due Sunday, so that's the only downside.
I think chapter 30 tomorrow works for me at least.
Yeah, I've done most of chapter 30. I got a little bit left, but yeah, that's tomorrow's fine.
Okay, that's cool. Just making sure. All right, guys. Well, let's get into chapter 31, which is, again, is another instance where I will do an abbreviated version. This is another chapter that a lot of people just don't even cover. A lot of my coworkers don't cover in it, but I think it's too important not to. It's where you start to put it all together. I don't do the derivation of the wave equation. I actually did that on my YouTube channel. You can check that out yourself. And I did it in what I think is a more appropriate way, and definitely well, it's more mathematical, but it's one of those things where I just use a rule that from mathematics that you can easily prove if you wanted to. Then I can put the equations together and I get basically a wave equation for the electric magnetic fields. And you can see where the velocity comes in, what parameters make up the velocity that it is, the speed of light, and all that good stuff. So I definitely recommend you checking that out. The one that your textbook author does is really ingenious and takes a lot lower level of mathematics, but it takes a lot more understanding. So in that sense, it's harder. And that's the nature of it. You know, we have a lot of cool maths that make problems easy. But if you don't know the math, then you don't get to do the problem the easy way. So you can look at the books version for the hard way with easy math, or you can look in my manual or my YouTube channel for the easy way using the quote unquote hard math, which really isn't. It's a matter of, you know, knowing an identity from cross products and vector calculus to some extent, but not necessarily. So with chapter 31, what we're doing is we're going to piece together what Maxwell's equations are, because we sort of have them. We have a Gauss's law, we have Ampere's law, we have Faraday's law. It turns out there's a Gauss's law for magnetism as well. It's not quite as exciting as the Gauss's law for electricity that we found. And it turns out that Ampere's law is left wanting. You might have figured that out already, just because I told you guys how magnetism and electricity are sort of two sides of the same coin. And you see that in Ampere's law, you have a closed integral of B dot dl is equal to mu 0 I. But in Faraday's law, you basically have a closed integral of E dot dl equals negative n d phi dt, right? Okay, so that means if you have a changing magnetic flux, you get an electric field. But on the other side, there's nothing about a changing magnetic flux that could create a magnetic field, or excuse me, a changing electric flux that could create a magnetic field. And that seems like an asymmetry, like something that we would expect. If Mr. Younger says that B and E are two types of the sides of the same coin, then you'd expect that. And that was something that Maxwell saw as well. And of course, he actually figured out a way to derive it. So I'm going to start off with just showing you that. So let's get started. I'm going to turn on my document cam. And what we're going to do is we're going to imagine Ampere's law as it is, and then look at a problem that Ampere's law leaves us with. So Ampere's law is the closed integral of B dot dl is equal to mu 0 times I enclosed. And sort of as I enclosed inside of some loop. This is really badly focused. It's I enclosed in some kind of loop. And for instance, when we had a wire going like this, the current going this way, then we could take an Amperian loop that was centered on the wire. And we sort of imagine the current going enclosed in that loop and piercing a surface that spans this loop, right? And that was fine. That ended up giving us B times 2 pi r, where r is the distance out here, is equal to mu 0 I. So we ended up getting B is equal to mu 0 I over 2 pi r in the theta hat direction. And that was great. Well, what about this scenario? What about we have a wire going like this with a current going this way, using the right-hand rule, of course. We'd want to use an Amperian loop that comes out and in front of the wire and then back behind the wire like this. But what if that then ran into a capacitor? Like this. And you had the other side of the capacitor right here. Now, when you do that, you definitely get B equals mu 0 I over 2 pi R using this surface as if it's being penetrated. But what if we took a sack and made that the surface? You have no current flowing through there. So you get the closed integral of B dot dl over the sack is equal to 0, but B is not equal to 0. So that was the problem. Well, Faraday looked at it this way. He said, well, it turns out that I can use the idea of a capacitor and sort of work out what makes a current in a capacitor, just, for trial and error. And maybe I'll get a formula. And if I get a formula, then that'd be great. And if that formula happens to work out, that'd be great, even though I derived it from something that wasn't really what it should have been derived from. So if you use Q, remember C is equal to Q over V for a capacitor. So if you use Q equals C times V, you can say, well, I know for a capacitor, the capacitance is epsilon 0 A over D, where epsilon 0 is the permittivity of free space, and D is the separation distance between the capacitor plates, and A is the surface area of the plates, right? So that's my C. And then, of course, your V is actually, remember, it's uniform in a parallel plate capacitor. So it turns out the E is just, the V is just the E times D. So there's my C, there's my V, and I got that. Well, in some sense, this left-hand side needs another current, and that current would be something related to a, sort of like Faraday's law, where we had a closed integral of E dot dl is equal to negative n d phi E over dt. That was d phi B over dt. But maybe we need something like this. So on this side, I have a mu 0 times a current. On this side, maybe I could have something that looks like a current and just put a mu 0 in front of it, and then the units would work out right. So when I think current, I think dq dt. So when I take the derivative of all this, you can see that pretty much I end up just getting basically epsilon 0. Notice the d's cancel out, and I get d by dt of A times E. Well, if you remember, the electric flux is equal to the integral of E dot dl, or excuse me, E dot dA, like that. So that really looks like a derivative of flux. So you could actually call it epsilon 0 d phi E over dt. So we're now going to try this and say, what if Ampere's law is actually the closed integral of B dot dl is equal to mu 0 I plus mu 0 epsilon 0 d phi E over dt? Well, it turns out with that little trick, Faraday made Ampere's law correct and internally consistent. So that's the new version of Ampere's law. So we call that, say, Ampere's law with Maxwell's correction. So like I said, Heaviside goes and writes all these equations in the way that we use them now and more or less advanced vector calculus. But he continues to call them Maxwell's equations because Maxwell was brilliant enough. He came up with all this stuff just from reading the writings of others and translating them into math and then making parts of it internally consistent. And then he went on to, of course, derive a wave equation that gave us an idea that there would exist electromagnetic radiation. And then Hertz found it while everybody else was looking for it as well. Hertz happened to run across it by himself. And that sort of nailed the final nail in the coffin of the people that didn't believe in action, or that did believe in action at a distance instead of fields. So that's how Maxwell corrected Amperes law. So let's look at a particular problem of this sort. And this is sort of like problem 31.3. So let's say we have a capacitor. This is going to be example 1. So let's say we have a 60 picofarad capacitor. Is being charged up. Ow. Let's say it has a plate area of 100 square centimeters. I'll put a dot after that so it seems like it's at least 3 sig figs, and is connected I'll say 2 is connected to a 100 volt, I'll put a dot after that too, battery. And a 4.0 ohm resistor. So first off, what I want to know is the way to change the electric field. Whoa. All sorts of bad stuff happened in there. B, I want to know what the current is. And C, I want to find the magnetic field induced. I'm going to assume this plate, by the way, it's a round parallel plate capacitor. So the parallel plate capacitor is going to look like this. Where this is a surface area A, that's a distance of separation D, and it's just air in there. Okay. So let's first off recall that we found an equation for when you start to charge up a capacitor, the charge in the capacitor. So this is our solution. The charge in the capacitor is given by C times V times, so Q is equal to C times V times 1 minus e to the negative t over RC. I think that was right. Yeah, that looks right. And we'll call this, actually, we'll say we'll call this V0 so it won't be confused with the voltage as a function of time. And from this, we can start to look for the electric field, because to find the electric field, because we're looking for what is the rate of change of the electric field, we're going to have to find basically the charge on the capacitor. And then, of course, once we have the charge on the capacitor, we can find the capacitance. And with the capacitance, we can find the electric field. And then we can take the derivative of all that. So if I first off take dq dt, you can see that the CV0 times 1, the derivative of that with respect to time is just 0. But the C times V0, I take the that is multiplied by a -1, because that's right there. Now I take the derivative of all this. That gives me -1 over RC. So that becomes positive over RC times e to the -t over RC, which I think you can see is equal to just V0 over R. And actually, when I asked for this, I'm really wanting to know what is it at t equals 0. So I should say at t equals 0, and say at t equals 0. Okay, so when we let t equal 0, then that implies I of t equals 0 is just V0 over R. So we get I of 0 is equal to 100 volts over 4.0 ohms, which is 25.0, carrying one extra digit, amps. That turns out to be part B, which we didn't necessarily want to get first, but we did. Okay. Now, now that I have that, I can go ahead and look for the electric field. So the electric field is equal to sigma over epsilon naught. And we know that just from, remember when we calculated the electric field near a plate, it was 2 sigma over epsilon naught. But then when we put the two plates next to each other, with one being positive and the other being negative, the two complemented each other and added, sigma over 2 epsilon naught plus sigma over 2 epsilon naught, and that gave us electric field in between. Well, that, by the way, is just the charge over the area divided by epsilon naught. So if I want to calculate dE dt, then I could say dE dt is just equal to 1 over epsilon naught A times dQ dt. So with that, you can see now, this is, basically why I had to start with part B first, was because I had to get dQ dt, which is actually the I. So now I've got 25.0 amps over 8.85 times 10 to the negative 12th. And remember, this was originally, this one was in the bottom of Coulomb's law, so it became meters squared, or excuse me, it became newtons should be in the bottom. Meters squared should be in the bottom, and then Coulomb squared should be on top. And that's, of course, coulombs per second for the amps. And then I have times the area, which is 100 times, notice that 1 square centimeter is equal to 100 centimeters to 1 meter squared. So in other words, I have to divide that by 10,000. So when I do all this, I get the time rate of change of, and that should be part A. The time rate of change of the electric field is just all that mess that I wrote there. So now let's calculate it. I got 25 divided by, now I'm going to do parentheses, 8.85 e to the negative 12 times parentheses 100 divided by parentheses 100 times 100, and just make sure they write 100 centimeters in the bottom. Yeah, that's going to cancel out with centimeters on top and then square it right. Okay, that's good. and I get 282.5, which actually gives me 2 extra sig figs, times 10 to the 12th volts per meter per second. So that's a pretty big amount of electric field. Remember, the electric field is measured in volts per meter. It also used to be coulombs per, newtons per coulomb, but it's also volts per meter, and that's a better unit for us to see here. But you can see it's literally about 10 to the 12th, which 10 to the 6th is mega, 10 to the 9th is giga. So 10 to the 12th is, I think we use tera for that one. So that's a really big unit. Anyways, so that was part A, and now we've already done part B. So what we want to do is find the induced magnetic field. Well, what you're going to look at here is you're going to have a circular, and this is the whole reason why I used a circular capacitor. You're going to have a circular disc for the capacitor, and maybe the electric field points in to the disc, or maybe it points out of the disc. It all depends. But the main thing is, once you have that, then you got to stick with whatever it is. But it's going to be a uniform electric field going across this. Now, from the fact that the closed integral of B dot dl was equal to mu 0 I, and the I, of course, was driven by electric fields pushing this way, then it seems reasonable that you would get a magnetic field pointing around here in this case, right? So that's actually the case. What we'll do is we'll imagine an Amperian loop again. And actually, I should do it this way since I drew the electric field pointing in, because the electric field pointing in means the current's going that way. So when I do my right hand like this, I see that the loop's got to go around this way. So what I can get is that the closed integral of B dot dl is not equal to mu 0 I, but rather it's equal to mu 0 epsilon 0 times d phi e over dt. The area is not going to change. So in fact, the d phi e over dt is just going to be A times the dE dt. So from this, I can get B times 2 pi r, where this r is the Amperian loop. B times 2 pi r is equal to mu 0 epsilon 0 d pi r squared. Again, E, we'll call this whole thing a big R for the radius, d of pi r squared E over dt, because that's the really derivative of the flux. But again, pi r squared is not changing. So I'm going to get, and this is equals, I get B is times 2 pi r is equal to mu 0 epsilon 0 pi r squared times dE dt, which is basically what we needed to be able to come up with this magnetic field caused by this thing. So ultimately, I can say that B, getting rid of this 2, actually there's no 2, getting rid of this pi, getting rid of this r and one of the r's over here, what I see is B is equal to mu 0 epsilon 0 over 2 times just plain r dE dt. So that, and of course it has the same direction that we found before. If we actually want to go out for r greater than r0, or excuse me, r greater than big R. If we want to go out further than that, then we'll still have the Amperian loop. and it'll still be concentric, and it'll still be going around this way. So we'll get B times 2 pi r is equal to mu 0 epsilon 0. But in this case, you only have an electric field, or excuse me, a magnetic field existing out to big R. So in this case, it's going to have to be pi r squared dE dt. And from that, you get, again, the pi cancels out here. This is for R less than big R. And notice neither one of these R's cancel out. So in this case, I get B is equal to mu 0 epsilon 0 R squared over 2R times dE dt. So again, we get a concentric type magnetic field, not unlike what we were finding using Amperes law with the mu 0 I term, but with the mu 0 epsilon 0 d phi dt term, we still get the same thing, just as in terms of the changing electric field, which obviously is not going to be, I mean, the dE dt was a really huge number, but it's not necessarily going to make for a really super large magnetic field. But you could find, for instance, let's take the actual values we have. All right, I'm running out of.
I'm sorry, I'm not understanding how the little r got into the denominator.
Okay, so remember we always had left-hand side equals right-hand side, and then you solve for B. So basically this time the R didn't cancel out with this R because they're different R's. The R is the radius of the Amperian loop, and the big R is the radius of the circular capacitor disk.
So the first equation, the first circled equation has nothing to do with the, like, it's separated from the second circle equation?
Yeah, so what you'll see is on the actual R equal to big R, they would probably be about exactly the same, because there shouldn't be a surface charge there. So they're continuous, but yeah, it's a piecewise function. It's this until it gets to big R, and then it's this when it gets out there. Does that make sense?
Yep, I got you.
Okay. Now that we have that, we can at least get a rough estimate of what it's supposed to be, because we already calculated what dE dt is. So let's get an actual calculation of how big this magnetic field is. So B, we found, was mu 0 epsilon 0 times R0, or actually, sorry, I keep reverting back to the notation that your book was using, but it's actually times the plain big R over, actually, yeah, it'll be about the largest actually at R equals big R. So I'm going to do this one over 2R like that. And then I'm going to do dE dt. So this will be the max magnetic field, meaning this is the, you might suspect looking at this is linear. So the magnetic field is going to increase linearly as we get larger and larger. And then when we get to R equals big R, it's going to start to fall off like 1 over R. So the maximum will occur right there at the edge. And we could estimate what the radius would be. So for instance, if we know that it's pi r squared equals 100 centimeters squared, we could say that R is equal to, let's say, 3.14159 divided by 100. Oh, I actually supposed to do that upside down. I actually won't 100 divided by pi. So I get 31.83 basically. Now I'm going to take the square root of that. And I get 5.64 times, it's 5.64 centimeters actually. So that's 5.64 times 10 to the negative 2 meters. So now I can put all this in. I'm going to say 4 pi times 10 to the negative 7th. That's Tesla meters per amp times 8.85 times 10 to the negative 12th. Again, this one's Coulomb squared per Newton meter squared times, in this case, it's only one of these going to survive, and I'll be up top. So I'm going to say 5.64 times 10 to the negative 2 meters times, now my dE dt became 282.5 times 10 to the 12th volts per meters second. All that divided by 2. So when I calculate all that stuff, 4 times 3.14159 e to the negative 7 times 8.85 e to the negative 12 times 5.64 e to the negative 2 times 282.5 e to the 12. All that divided by 2. And I get 88.6 roughly times 10 to the negative 6 Tesla. So not a very big magnetic field at all. But you know, it was a rather large dE dt, but remember that's happened in a probably decent amount of time, and that's just at t equals 0. So anyways, any questions on that? So that's just another way, like I said, of using Amperes law, only not with the mu 0 I, but with a mu 0 epsilon 0 d phi dt. Okay, and it puts our Maxwell's equations on sort of solid symmetric footing, where E and B actually play very, very similar roles. That's also called the displacement current. So you can also see the I displacement. The weird thing is this displacement current, they still use this terminology, but it's from an idea that someone had that didn't really pan out to be what they thought it was. So it's a little disingenuous to use it, but it's epsilon 0 d phi e over dt. And when you have that, you have closed integral b dot dl is equal to mu 0 times I plus ID. So that's sort of the advantage. You can write it just like another current, and it has units of current and all that good stuff. So the big deal now is Maxwell's equation. So here's Maxwell's equation in integral form. This is in integral form with SI units. Okay, it turns out that Gauss's law, the closed integral of E dot dA, is equal to Q enclosed over epsilon naught. So we'll just write Q over epsilon naught. It turns out there's a Gauss's law for magnetism. The closed integral, am I right now? So thank you. The closed integral of B dot dA is equal to just 0. Now, sometimes they'll call it Gauss's law for magnetism. Sometimes they'll just say there are no magnetic monopoles. That's more or less, if this equation is 0, that's more or less what it's telling you, is that you'll never have an isolated North Pole or an isolated South Pole. Because notice this created a magnetic field that diverged from a positive charge. It radiated outward. All magnetic field lines we've ever found have been complete loops. So we expect, since they're complete loops, this should be 0. But if we ever found one that just emanated from a point or just ran into a point, of course, that would be like a southern end of a bar magnet. Or if they emanated from a point, that would be like the north end of a bar magnet. If we found that, then this side couldn't be 0. So that's 2 ways of explaining it. Now, the other part is, of course, we have Faraday's law, which says the closed integral of E dot dl is equal to negative, and I'm leaving off the n here, d phi b over dt. But now we can see the equivalent to that, even though it's still just a little bit off, as you expect it to be, because these two are a little bit off, is mu 0 I plus mu 0 epsilon 0 d phi E over dt. So if you have no charge and no, which is the fundamental unit of electric fields in some sense, and if you have no current, which is in some sense the fundamental unit of a magnetic field, then notice these equations are exactly similar. You've got E dot dA is equal to 0. You got B dot dA is equal to 0. You've got closed integral E dot dl is different from by a sign of d phi dt, and closed integral of B dot dl is basically the same. Okay, but the difference, of course, is a mu 0 epsilon 0 constant. So that's Maxwell's equations in, again, in SI units and in integral form. They actually have them, and a lot of people will solve them preferably in the differential form. But that's obviously would require you to understand differential equations. And it's not only that, it's kind of a nasty version of differential equations, and that they're partial differential equations. And with that, you have to do boundary conditions, which you had to do with all of them anyways, but still. So now that we've covered that, we need to learn some fundamental things about magnetism and electricity. And one of the things is that magnetic fields and electric fields go hand in hand. And it's hard to show you that, but let me tell you this. So it turns out when Maxwell put his equations together in such a way that he got a wave equation, what he found out was that there exists some kind of wave that allows an electric field to oscillate in one plane, a magnetic field, which be comparing units of electric field to the units of the magnetic field, would make the magnetic field really, really small compared to the electric field, but in an entirely different plane. In other words, a perpendicular plane. And then perpendicular to both of those planes was a third direction. That was the direction in which it traveled. So it turned out that, in fact, he knew at that instant what light was. You can imagine this is a line coming out of the page. So this is supposed to be a line coming out of the page. Actually, I didn't mean to draw that long. Okay. And let's say the electric field is vertical. So it oscillates up and down vertically. So right here, it's about that big. Right here, it's about that big. On this side, it's about that big. And then it rapidly goes down to nothing like this. And then it goes to small, but in the opposite direction, big, slightly bigger, big again, small again, and then again, small. These are all supposed to be vertical. I don't know why I keep trailing off and making them non-vertical. Okay, so this is what's going on with your electric field. Now, perpendicular to that, in a right-handed way, is your magnetic field, and I'm drawing it way, way bigger than it is. Just so you can see it. And then perpendicular to all of that is this axis in which it's going this way, which is the velocity of the wave, which turns out to be c, the speed of light. Okay. So this is the electric field. This is the B field. And then the velocity is perpendicular to both of those. And it turns out that E over B is equal to the speed of light. So you can see, in order for the B, in order for you to get the electric field, you have to multiply the strength of the magnetic field times 300 million. That's why I meant the magnetic field is so much weaker than the electric field. But that's what light is. So when Maxwell did this calculation for a brief period of time, he was the only person to know on the entire planet what light was, which is really weird because we had just finished going through Newton, knowing that light was in fact particles or corpuscles of light, and it derived all of the equations that we use for optics and got them all right, by the way, because later Maxwell comes along, uses the equations of electricity and magnetism and the fact that electromagnetic radiation are waves, and he got the exact same equations that Newton did. So it's this weird anomaly in that Newton got exactly the same answers as Maxwell did, even though he treated it as a particle and Maxwell treated it as a wave. And I say Maxwell, but actually a lot of people did the other stuff showing it. So now that you have that idea of what light is, I can tell you about producing waves and antennas and stuff like that. So let's imagine for just a second, we have a little battery that's connected to a little bit of a circuit. So in fact, it's going to be a little battery connected to a switch, to a wire like this. And the switch can be opened and closed at will. What I want you to see is when the switch is finally closed, what's going to happen is you're going to get current flowing in this direction. Okay. Well, because of that, that's going to make a magnetic field, which remember we draw as red, as going into the page on this side and coming out of the page on this side and going into the page on this side and going and out of the page on this side. And that's your magnetic field. Now, at the same time, from what we just learned about this, that means our magnetic field, or excuse me, our electric field is going to in fact be perpendicular to that. And what we'll get is a electric field that does like this. Okay. And this will go on for some time this way, right? And this will start to, of course, move out that way. So as time goes by, this thing goes further and further out and then it stops. Now, what happens if we flip that battery over? If we flip that battery over, now we're going to have something different as well. We're going to have, in this case, we're going to have a current going this way, like so. And of course, that's going to create a magnetic field that is going out of the page or into the page on this side, which, by the way, now this has moved on further out here to be like this, and into the, out of the page on this side. And remember, our electric field, of course, is now pointing this way. And our magnetic field over here is still this way. But now that part's been released. So it's over here now. And in fact, what we ultimately get is a little kidney bean shaped thing pulsing out from this side, where we got an electric field going this way, all the way around to the circle in that way. And then we got of course, magnetic field lines going in here. Magnetic field lines going this way out here, because remember, that's the ones we originally drew over here. And of course, if you let this go continue, then it's going to get another one of these and another one of these and another one of these. And as you get really far away, ultimately what that'll look like. So let's go, a million miles away, say. Now what we're going to get is actual what we call plane waves. And that's generally what we study. We'll have electric fields, of course, oscillating this way. And then we'll have magnetic fields, of course, being this way. And then we'll have electric fields this way, and then magnetic fields this way. So what you're actually getting is electric field oscillating back and forth this way, and a magnetic field oscillating back and forth this way, which is just like that diagram is. So once you've made sense of that, now you can start to understand how we describe waves. And what we do is we say the electric field is actually equal to some magnitude, let's call it E0, times the sine of kx minus omega t, where k is equal to, remember, omega is equal to 2 pi f. Well, you can sort of look at that and say, well, f could be looked at as omega over 2 pi, or excuse me, omega could be looked at as 2 pi over the period. So this could be looked at as 2 pi over the wavelength. And of course, omega is 2 pi f. So we do that. Then we say, all right, well, B is equal to E0 sine, notice they're in phase, of kx minus omega t. And in fact, we're going to say that the electric field is going to oscillate in the y direction, and the magnetic field is going to oscillate in the z direction, so that we get then the velocity is in the x direction. Like that. So that's the way we model them. So you can take, you'll see a bunch of problems in this chapter that are really simple, like they'll say the wavelength or the frequency, or they'll give you both the wavelength and the frequency. And from that, they'll want you to write equation for the electromagnetic radiation. Well, the equation for the electromagnetic radiation is this in front of a j hat, this in front of a k hat, and of course, that's really what the velocity is. So the velocity is going to be related to that through a nice simple expression, basically, that you can see is f times lambda is actually equal to the velocity. And of course, the velocity happens to be also equal to omega over k. Okay, and that's going to turn out to be just the speed of light, which is c. So that's a lot about what this is about. And in fact, when Maxwell does his wave equation, what he found was V is equal to C is equal to 1 over the square root of epsilon 0 mu 0. So that 8.85 times 10 to the negative 12th we used earlier, and that 4 pi times 10 to the negative 7th we used earlier, when you multiply those two, take the square root and get the reciprocal, you get 299,792,458 meters per second, which is the speed of light. So that stuff I think is really easy. It's just a matter of you remembering that, and also remembering this little expression here, which will come in handy. But right that way I can see it now. It's that one right there. E over B is equal to C. So the electric field strength divided by the magnetic field strength is equal to the speed of light. And then these quantities and that can all help you fit stuff. So you can look, for instance, just to give you an idea, examples like 31.2 and 31.3, 31.4. So I'll say examples 31.2 through 4. Those are really, really remedial examples. Like all you have to do is just plug in what the K, the W is. Now, that being said, let me give you the neat part. So I've sort of mentioned this before in 241 as well as in parts of this, but the mnemonic I use for the parts of the electromagnetic spectrum is sort of homage to Rush Limbaugh in some sense, who I've always enjoyed listening to, but I can't say I'm really a fan or that I necessarily like him, but I just enjoy the show. So let's say great excess undermines various industries, Marxism rules. So that's the parts of the electromagnetic spectrum. This is gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio waves. And when you do it this way, the downside is you've got to use Vib Gior. And this is high frequency. This is short wavelength. And it also turns out to be high energy. And this side, of course, is low frequency, long wavelength, and low energy. So for instance, radio, like AM radio. So AM 850 implies that the frequency is 850 kilohertz. So whenever you see an AM radio station, you just put kilohertz after the number, and that'll give you the frequency. Similarly, FM 93.7, you should just say, okay, well, that's frequency equals 93.7 megahertz. So in other words, times 10 to the 6. So once you know that kind of stuff, then they can automatically just say, okay, well, what is the wavelength for AM 850? Well, we know that velocity of the wave, which is the speed of light, is equal to frequency times wavelength. So I just substitute that frequency in. I can solve for the wavelength. Turns out this one's like 4.5 football fields. Okay, so that gives you an idea. Yeah, that's long wavelength, right? This one's on the order of the size of a basketball goal, or the height of a basketball goal, I should say. So you can put that together. You can also, if you want to do a little deep dive into these parts, they actually labeled every factor of 10 a different number, like super high and ultra high and stuff like that, frequency. So we used to have UHF TV and VHF TV, not to be confused with VCRs and the other version of that. But basically, it's the frequency that they were talking about. Back in the old days, your TV had a knob like this, and then it had another knob like this. And this is where 2, 3, 10, and 13 would be way over here, right? But if you turned it to the 0 on here, then you could pick up 15, 27, 33. Those were all the UHF channels, and these were all the VHF. So this is this is CBS, NBC, and ABC. And these were, well, both of these were in some sense PBS, but this was also ultimately to become Fox. And then that sold out, and this became Fox, and that became Kids WB, and all sorts of stuff like that. But all of these are different parts of the spectrum, and you sort of need to know that. The only other part that I really think you need to know about this is, how do you calculate the energy delivered, in other words, the power per unit area for radiation, and what's the pressure delivered. So it turns out that there's this wonderful vector called the Poynting vector. So the Poynting vector. Turns out Mr. Poynting beat Mr. Heaviside to the punch on this one and actually published it beforehand. But in fact, Heaviside didn't see it and published it himself. And then, of course, apologized because he realized someone else had beat him to it. But they did independently discover it. But basically what you end up getting is that the Poynting vector S is equal to 1 over mu 0 times E cross B. So you can see already E cross B points in the direction of velocity. So yeah, this S vector points in the direction of velocity, but it actually gives you the power per area. It literally comes out in units of joules per second per square meter. Okay, so for instance, the Poynting vector for our sun, this is a very typical problem that we learn about in various levels, whether it be introductory astronomy or introductory physics. It turns out our sun, at least at our in our atmosphere, reaches 1,350 joules per second per square meter. So you can see that's 13.5 light bulbs that could be ran for every square meter of satellite dish, if the satellite dish, of course, was 100% efficient. Satellite dish, solar panels. Sorry about that. Solar panels are actually more along the lines of about 20% efficient right now. So if I divide that by 5, I'm looking at about 2 light bulbs could be run for every square meter. That's actually more impressive than you think. I'm talking 100-watt light bulbs, and 100-watt light bulbs suck up a lot of power. Okay, 100 watts basically is the power required to lift 100 red delicious apples off of the floor and onto the ground in a single second. Okay, so yeah, you can see 100-watt light bulbs, a lot of energy going into it. Also, if you want the pressure, so this is the power per unit area. If you want the pressure, and you can call that solar pressure, for instance. I don't know why I didn't know that. The pressure is actually about, well, it's related to the Poynting vector, so that makes it kind of nice. But it turns out the pressure is actually 2 times the average Poynting vector divided by the speed of light, c. So that's the kind of pressure, for instance, you can use to power a solar powered spaceship. So if you literally just put solar panels up as an array, like a sail on a spaceship, then you're going to get a pressure on this just as a result of this sun's power or sun's Poynting vector hitting it. And that can actually accelerate you rather quickly for nothing. So that's kind of nice. But that's the uses of this stuff. You'll see a lot of little neat conceptual type problems. I do more with this in the homework than I do with it in the actual test. I have simple problems like, you know, how much energy or how many square meters of solar panels do we need to supply a house with 200 amps, you know, for a month or something like that. So we can do stuff like that, but I'll do simple problems like that. I'll give you the efficiency of the solar panel, but that's about the most complex stuff. I get you to do that and then fill in the omega, the K, the E and the B on those equations for electromagnetic radiation. So E equals E0 sine KX minus omega T, that stuff. Any questions on that? All right, so this is what I am calling chapter 11 completed in its entirety, believe it or not. So does anybody have any questions on all that good stuff?
This seems like one of the more, this seems like probably the most straightforward chapter we've had in a while, in my opinion. Just
yeah, it's got really deep implications, but it's from a difficulty solving problem standpoint, it's certainly the most straightforward and easy. So hopefully that'll come off very easily for you. And it's really the best part about it is in the reading, to be honest with you. So you'd be selling yourself short if you don't actually read this chapter, because this is where it brings it all together to make all of it make sense. Even if you don't understand all the derivations in it, if you could read this chapter, it would be the most valuable for you to read to sort of get a big screen perspective or a big view of the entirety of 21 through 29 and 30. So I would highly recommend reading it. Definitely just make sure you do these problems. It won't be that bad, though, and the test will be even easier. So you guys are free to go. If you have any questions, go ahead.
Yeah, just a quick question on the test. So I know you sent an email out. I don't know if that's still fully accurate. So I think if I remember correctly, the four test is going to be out Wednesday and due Friday, and then the fifth test is due Sunday, if I remember correctly. Or
yeah, I'm going to go ahead and basically make. I think what I'm going to do is I'm going to make the test 4 available now, and then I'm going to make test 5 come open on Friday. Test 4 will be due Sunday. Test 5 will be due Wednesday.
Thank you.
No problem. I'm doing it right now as we speak, so I won't forget.
And it's the same thing where we have 3 tries?
Yep. Same old ditty.
I have another general question.
Okay.
Thursday is Veterans Day, but we still have class, right?
Yes, I did not see a cancellation for that.
Okay.
Of course, I don't mind if you guys miss class. I understand that completely. And you don't lose any points or anything crazy like that. So, today, but I'm definitely holding class just in case there's some ambiguity in the answer that I didn't intend. Okay, so today's the 9th. I'm saying the test 4 will be due on the 14th at 11:59 p.m. And I'm going to do save and publish. Now I got to go back in and edit it to put the right date in the stupid box because I'm a stupid head. Anybody else have any questions while you're sitting here waiting?
Oh, and are we moving on to the teens now? Like 17, 18, 19 chapters after this?
Yes. Yeah, that's the next set that we go for.
Okay.
Okay. Anybody else? All right, I just set test 4 available and corrected the date on it. Now I'm going to do the same thing with test 5, and that'll be due the following Wednesday. But I really recommend you get both of them done by Sunday because you'll forget the Wednesday. Yay, isn't it fun to be in physics? There's so much more things we could do. This test 5, I'm editing test 5. This is going to be now due on, move it to November. Let's do November 17th at 11:59 p.m. November 17th at 11:59 p.m. Oh, we're too far.
And you're also going to change the mastering physics so it wasn't due today, correct?
Yes, I will do that too now. Okay, I just finished the test 5 thing. Let me go over to my lab and mastering since y'all cracking that whip on me. Let's see, what is listed as being due today? I'm looking. You're looking. It's going so slow. He's out. He's out of the pen.
Oh, I know. I'm watching it. There's for the cat play.
All right, guys, hold on. Let me check, see what's due. It looks like, so conceptual wise, 1027 is past due for chapter 29. Chapter 30 was 11:1. I was okay with that. 31 I made to 11:17. What is today? 11:9. I don't see any 11:9s there. Let's see in the homework part. We got 11:1 for 29. 11:8 was for chapter 30 homework. 11:10s for the next one. Actually, I'm gonna put homework part 1. No, I think that's good. Homework part 2 is supposed to be 11:10. Y'all said y'all were good with that, so I'll leave that be. 31 is 11:15, 11:17, 11:24. Yeah, I don't see anything being due tonight.
Well, no, actually, it was set for 11:59 a.m., so it might be past due. I don't know. If you
Okay, for like yesterday or something. Oh, I do see some AMs over here. Well, that bites. I'll fix that one. I'll fix that one. I'll fix that one. Okay, now I'm just looking for anyone that has an AM instead of a PM. I think I just saw another one. That's what it was, yes. And that's 39 conceptual. Heck, since I screwed that up, let's go ahead and change that to okay, so there's 2 conceptuals that were doing 11:9. That was 39 and 20 for some reason. I don't know why 20 was there, but anyways, I changed those both to 11:1, 11:59 p.m. And I think that fixes everything for those. And I don't see any other AMs over here. I don't know how that even happened. There's some mess load at the end. All right.
Thank you. Have a good afternoon.
No problem. See you, Clarence. I just said that like I'm all confident knowing his name. What will?